So hello everyone, we'll be starting with the tutorial on state feedback part 2 of the linear dynamical systems. So these are the questions which we would address in this tutorial. The first two questions deals with the design of the cyclic design of the controllers. The third is the state feedback design for the multi-input systems. So in the tutorial part 1 we had seen mainly the state feedback design for single input system. In this tutorial, we will also see the problem of the state feedback and the disturbance rejection controller, which we have also defined as a robust controller. And we will also discuss the linear quadratic regular problem in this tutorial. So in the problem 1, given a plant defined by the pair AB, where AB matrices are given by this. So the first question we need to address to find out whether the matrix A is cyclic or not. And the second part of the question is, can a state feedback controller be designed using single input variable control design method? Okay. So now recalling the lecture slide, we have defined a matrix A, a cyclic matrix, whenever the Jordan form of A has one and only Jordan block associated with each distinct eigenvalue. So for the given matrix A, we can first compute the eigenvalues, and we see that the eigenvalues are the repeated eigenvalues at -1, which forms two Jordan blocks of size 2 cross 2 and 1 cross 1. So according to the definitions we had introduced in the slide, the matrix A is not a cyclic matrix. Okay. Now the second result says that if the pair AB is controllable, then for almost any P cross N real constant matrix K, the matrix A minus B times K has only distinct eigenvalues and is consequently cyclic. So first of all, we need to check the controllability of the pair A comma B, and this we can do this by computing first the controllability matrix and then finding out the rank of that controllability matrix, which happens to be 3 here, which is equivalent to the dimension of the A matrix. So we ensure that the pair A comma B is controllable. So recalling again this result, it says that for almost any real constant matrix K of appropriate dimension could ensure the cyclicity of the matrix A minus B times K. So here we select K as any arbitrary matrix, is this one, and then computing A minus B times K, which happens to be this matrix, and we can write this into the Jordan canonical form in this. So we see that all the eigenvalues are placed at the diagonal, and therefore this matrix is a cyclic matrix. Okay, now just for the verification, you can also select another K matrix and again verify whether for the matrix K what you have selected is this matrix A minus B times K is cyclic or not, because we have already seen that the pair AB is controllable. So it means that there exists more than one K matrix. Now the problem 2. Again we are taking a pair A comma B. So the first part remains the same, where we want to check the cyclicity of the matrix A, and here we are now introducing a vector V 1 comma 0, and now we want to comment on the controllability of the pair A comma B times V. So we are discussing these two problems so that finally we can design the multi-input controller. So the first definition remains the same of the cyclic. We just compute the eigenvalues of the given matrix A, which happens to be the distinct eigenvalues. So it is already ensured that the matrix A is a cyclic matrix. Okay. Now there was another result which we also discussed, that if the n-dimensional P input pair A comma B is controllable and if A is cyclic, so you can also check the controllability of the matrix of the pair AB, and by computing the controllability, by computing the rank of the controllability matrix, which happens to be 3. So this pair is controllable. We have already seen that the matrix A is cyclic, so it implies that for almost any vector v, the single input pair a comma b times v is controllable. So here in this problem, the v vector is given to us as v equal 1 0. So we can numerically verify this as well, that if I compute another pair a comma b, because now this b would be a vector, and if this b is a vector, we know that the controllability matrix would be a square matrix, so which you can see here, and again the rank is 3. So we have verified this for this v, which is given into the problem. Now you can also take another v vector and can verify whether with your selected v vector this a comma b pair is controllable. Okay. Now this problem 3 deals with the state feedback design. So whatever the results we had seen in the first two problems, we will apply here and finally compute the matrix K, the state feedback gain. So here A, B matrix are given to us, where A is a 4-dimensional and B is a 4 times 2, meaning to say that we have two inputs, and we want to design, or we want to synthesize the constant matrix K such that this matrix A minus Bk, which is the state feedback matrix, has eigenvalues located at these 4 locations. So before coming on to the solution to this problem, we would recall a couple of points. So here we see that the system contains two inputs. Now if the system is only single input, we know that the state feedback gain matrix would be unique. But since we have two inputs, we cannot ensure the uniqueness of the constant matrix K, although many of these K matrices would put the eigenvalues at these locations. Okay. So here we would use the cyclic design to synthesize this state feedback gain matrix. So given this pair A, B, first we can check the controllability matrix, and since the rank of this controllability matrix is 4, the pair AB is controllable. Now writing the Jordan form of the A matrix, which is given by this. So we see that all the Jordan blocks are of size 1 cross 1. So the matrix A is cyclic, the pair A comma B is controllable. So we can select any B, what we had done in the problem 2. So first of all, we select the B vector as 1 and 2. We can calculate the controllability matrix of the pair A comma B times V. And one of the results we had seen earlier says that this pair would also be controllable. So this pair is a controllable pair. So now we can proceed forward to design the state feedback controller for the reduced single input system A comma B times V. The state feedback gain vector K, because we want to synthesize this is a vector K, so that the eigenvalues could be placed at these locations, and we can do this by using the eigenvalue assignment method we had discussed in the lecture, or you can use the place command in MATLAB as an alternative. So this K vector we have computed. Now this is for the single input system, and the single input system is where we have taken this B as capital B times V. Okay, but we want to synthesize this K, and we can do this by computing the original control input signal U as V times U dash, where U dash is now minus K times of X. Okay, so now if we compute this K1, which would be the multiplication of this V vector or V column vector and this K row vector, so we can compute this K1 matrix. Okay, now you can also compute the eigenvalues of this matrix by plugging this K1 matrix here. You would see that all the eigenvalues are located at these 4 locations. Now the second matrix second state feedback gain matrix we can compute by selecting another arbitrary vector v, column vector v, which is we have selected here as 0.8 and -1. Then following the same procedure, first of all computing the state feedback gain vector k for a reduced single input system, and then computing k2 as the multiplication of the column vector v, what we have selected here is, and the row vector k, what we have computed here. So this would be another state feedback gain matrix. Again, you can compute the eigenvalues of the state feedback matrix by plugging this k2, and you will see that all the eigenvalues are placed at the desired locations. So in this problem we would see the 2 points. First of all, we will design the state feedback gain which ensures the stability. Second, we design the feed forward gain such that the another objective, which is the tracking objective, can also be fulfilled. This is part A. And in part B, we would see that if there are some external step disturbances happens to be on this system, then how the response of the closed loop system would behave. Okay, so first we will deal with this part A, where we want to place the desired eigenvalues on the left hand side, and the output should track a unit step input, which is r is equal to 1. So for the given information A, B, C, we can calculate these eigenvalues. We can calculate the desired feedback gains for the eigenvalues, this one. And there are a number of methods we had discussed, because again this is a single input controller design. So you can use either of the design method, either the eigenvalue assignment approach or the Lyapunov design based approach. Okay, but here there's another way what we are following here, which is which you can do if your system is or having a dimension 2. So we want to design this state feedback vector k. So suppose we have designed this k, and if we compute the desired eigenvalues of the state feedback gain, it should be equal to the desired eigenvalues. So now if we compare the characteristic equation, so this part should be equal to 10 and this complete part should be equal to 26. So now we have two equations, two unknown as k1 and k2. So if you plug these k1 and k2 here, you would get the desired eigenvalues located at these locations. Okay, so computing this k1 k2, we computed 12.99 and -1. So once we put this k into the closed loop stability has been ensured, but it is not yet guaranteed whether the output would going to track the reference signal. For this, if you recall the lecture slides, we need to investigate about the transfer function or the DC value of the feedback system. This we can do by computing the transfer function and then computing the value of the transfer function at s is equal to 0, that is to say the DC value or the steady state value of the transfer functions. So the transfer function can be computed by using this formula, where we know all these vectors and matrices C, A, B and B. K we have computed. So we see that the closed loop system is given by this. So the steady state value of the output y, you would see, is given by 1/13. So even if you are supplying the reference signal r is equal to 1, it won't be able to track only with this state feedback controller. We need to provide feed forward gain. So the control input or the control law would change to PR minus k times x, where k we have computed, which ensures the stability, and now we want to compute the p such that r would become equal to y. Okay, so since we know the DC value, and we can put the DC value as the inverse or as the inverse of this value, which is 13, to make the output track the unit step input r is equal to 1. This we can see in simulations also. that once I put the controller as u is equal to PR minus Kx, the output of the closed loop system tracks the reference R is equal to 1, and this is the control signal. Okay. Now the second part of this problem deals that if there is some disturbances acting onto the system, whether the we need to identify whether the output is still able to track the reference signal. So this you can do in simulations also, that we have added a step disturbance at t is equal to 4 seconds to the system, and the step response or the output of the system is now given by this. So at that time when the disturbance was inserted into the closed loop system, the output was not able to track the reference signal, okay, due to this external disturbance. So disturbance has some predominant effect onto the closed loop system. So now we want to design a controller. You can call it a robust controller or a disturbance rejection controller, so that the effect of the disturbances onto the closed loop or the response of the system can be nullified. So if we recall the lecture slides, where that is 29, on which we have discussed another closed loop architecture which ensured that this external disturbance or the effect of this external disturbance onto y would be nullified. Okay, so the two design parameters are k and ka, and to design this, first of all we compute another pair which is nothing but the augmented pair with the original system and with this, because with this integrator, because this integrator would now become a part of the plan, and this happens here. So here we computed two different matrices A bar B bar, and now we can calculate the feedback gain vector for this new pair A bar B bar, and we can partition it as k and ka, where k, this part, is the feedback one, and ka, which is being acted onto the forward path from the reference signal. Okay, and you can design and you can use either of the method, the eigenvalue assignment method or the Lyapunov-based method. So now if we pay attention to the closed loop signals of the system on which the disturbance is being acted, so you see when the disturbance is being added at t is equal to 4, the output almost tracks the reference signal now. Okay, because of this new structure we are able to reject the effect of the disturbances on the output signal y, and this happens, we know already implicitly, because of this integral action, which is able to diminish the error between the reference and the output. Okay, so this problem 5, it's we want to compute the feedback invariant. So here we have considered a non-linear system, whose generic representation can be given by this x dot is equal to fx comma u, which is a non-linear system, and there are some properties associated to some function b which we are introducing, that a continuously differentiable function b with v of 0 is equal to 0. Okay, we need to verify or we need to validate that whether this function h, defined as this one, is a feedback invariant as long as the xt is equal to 0 as t tends to infinity. Okay, so this problem was taken from the book by Jao Espanaha, and this problem is exercise number 20.1. Okay, so recall from the lecture slide number 56, we have defined a functional h as a feedback invariant whenever if when computed along a solution to the system, its value depends only on the initial condition and not on the specific input signal. So this is how we define any functional which involves system input and state as a feedback invariant. Okay. So we have provided this functional h onto the left hand side, onto the right hand side as the integral from 0 to infinity, the partial derivative of v with respect to x, and a function f x comma u dt. Okay, so we want to show that this function is nothing but a function of only the initial condition and not on the or it does not depend on the specific input signal. So first of all, we will treat this v, or we do some analysis on this v to reduce the integrand for better visualization. So the derivative of, if I compute the derivative of v along the trajectories of the nonlinear system, which we denote by v dot x, it is given by as, because v is a functional, okay, and which depends from x1 to xn. So I need to compute its derivative with respect to each x, and since v is a function of x, it would be multiplied by the derivative of x itself. Okay, and it should be summed up because v, if you see in the definition, it maps from n space to r, rn to r. Okay, and we know that x dot I would be equal to fi of x, where f is a vector differential function. So I can represent this summation as this row vector and this column vector, which finally could be written as del v by del x dot fx. Okay, so the derivative of v along the trajectory of a system is dependent on the system equation. Now you would see some similarity. So this part would now happens to be equal to this part, right? Let's see in more detail. So consider again this one. I can write this whole part, what we had seen, as equal to v dot of x, and if I integrate this v dot, I would get v of x at infinity minus v of x at 0. Okay, so now if I use this condition that my x would become equal to 0 as t tends to infinity, so this inside part would become equal to 0, and I know from the property of the function v that v of 0 is equal to 0. So this part would go away and the remaining part is v of x at 0. So by computation we see that this functional h depends only on the initial condition. So this is a feedback invariant function, and it becomes a feedback invariant function only under this condition, otherwise it won't be possible. Okay, and this, if you recall, it is similar to the condition of asymptotic stability, right? So the last problem is about the linear quadratic regulator problem. So we are provided this state space system, which is a single input and two state system, and the performance index is now given as here. So far we have considered about the performances as the stability or the tracking. Now here the performance index is given by, but with this particular cost function, and we want to obtain a feedback control law which minimizes this performance index. This is the first part. Now the second part is that with respect to different input and state weighing matrices, we want to compare the dynamics of the state and input signals. Okay, so let's see, if we write our problem into the standard form as we had seen into the lecture slides. So that matrix A, vector B, this Q would be a state weighing matrix, and R, since we are having a single input system, so this is a scalar, and T naught is equal to 0. So you can quickly verify that this system is an unstable system by computing the eigenvalues of the matrix A. Now if you recall the linear quadratic regulatory control design, this controller is given by this equation, which is optimal, minus 1 by R B transpose P times X. Okay, where P is a 2 by 2 symmetric matrix, which you can write it as this, and you can compute by solving this algebraic Riccati equation, which we have derived into the lecture slides. Okay, and this you can also solve by using the KR command, by using this command in MATLAB. Right, so now we would go directly onto the simulations, because this information is already given to us, A, B, Q, R. Now using this information, by using the derivations we had seen into the lecture slide, you can compute directly this control law, where P you can compute by this one. So A and B are fixed because of the system dynamics. What we can see the behavior of the closed loop system with respect to Q and R, which are the state and the input weighing matrices. So we consider two cases. In the first case, we denote it by Q1, which is the given one, and this as R1 as 0.25, which is 1 by 4. Okay, in the second case, we take Q2 as 4 times of Q, and we keep R2 as equal to R. So first of all, before seeing the simulation, you should understand that what you are expected to see. If we go to the physical significance of this Q, or the significance of this Q matrix and R, it defines the state, the weighing matrices. So if I increase this weight, which I am increasing in the part 2, or in the second case, meaning that I am expecting my state to go to 0 as fast as possible. I am putting more penalty to the state variable. Now if I am putting more penalty to the state variable, it implicitly means that my control signal would be more aggressive. So in scenario 2, I predict to see an aggressive control behavior as compared to the case 1. Okay, so by putting this Q1, Q2, R1, R2, we simulated the scenario, and this blue signal is the U1 and this orange signal is U2. So as we have predicted that U2 would be more aggressive, because the state trajectories need to reach to 0 as fast as possible. Okay, and the same behavior we would expect in the state trajectories, that this state trajectories, which is the first state trajectory of the case 1, and this state trajectory, the first state trajectory of the case 2. So this reaches to the 0 as faster than the first case. Similarly, the second state trajectory. Okay.